This video deals with the colors of transition metal solutions. Let's begin by considering an aqueous solution of copper sulfate that has a characteristic blue solution. We begin by shining white light onto it, and I'm representing white light here as a mixture of red, orange, yellow, green, blue, and violet. Upon leaving the container with the copper sulfate solution, only 5 colors emerge. The orange is missing, and this combination produces blue light. How do we know that orange is the color that's removed? For that, we can consult the color wheel in our IB data booklet. Here I've provided the colors rather than the wavelengths. If something appears blue, if the color of our solution appears blue, then the color opposite it is absorbed. So the copper sulfate solution absorbed orange. Why orange? Well, let's begin by looking at the arrangement of electrons in the d orbital of a copper +2 ion. Now this copper +2 ion is in the presence of water molecules, and these water molecules, in fact 6 of them, can bond by means of a coordination bond, where an unbonded pair of electrons for oxygen are attracted to the +2 ion. This results in a splitting of the d orbital into 2 energy levels. This water molecule is sometimes referred to as a ligand. A ligand is a substance that has a pair of electrons that it can donate to a metal ion. And here are some other common ligands. When the d orbital splits, an electron now can move from the lower d orbital to the high d orbital, but that requires energy. In this case, an orange color of light would provide sufficient energy to make that jump. Therefore, removing the orange color as it has been converted into the movement of our electron. The size of the gap or split determines the energy of the absorbed color. If it's a small gap, that requires a small amount of energy with a large wavelength, perhaps red or orange. If the gap is much larger, we require more energy, something with a small wavelength like blue or violet. The size of the gap can also be affected by things like the ion involved, its charge, the ligand involved, and the number of bonding ligands, which is usually 4 or 6. Let's try a question dealing with this concept. The absorbance spectrum of a titanium solution shows a very high absorbance at 520 nanometers. What color would this solution appear? So I begin by consulting diagram 15 in our IB data booklet. I locate where 520 nanometers would be, somewhere here in the green region. I then observe the color that's opposite to the green, the red. So this solution would appear red. I hope you found that useful. Comments are always welcome. Thanks for watching.